For example, right in here would be Southwest 74th, and this would be Southeast 79, Southwest 79, so right at 104. So this tornado is moving right up into densely populated areas. In fact, it's in it right now. We've seen some incredible damage path, maybe a mile wide, maybe longer. Check with Bobby on the tornado at Okarche. Do we still have tornado at Okarche? Okay, as you look at it, this tornado is moving through parts of Newcastle and southwest Oklahoma City. Now that would be close to circulating southwest 149th, South Meridian Avenue, South Portland. It's moving over northwest 24th Street in Newcastle. Newcastle area could be very hard hit with this particular.
This is the story of a tornado that science almost missed, and how 14 minutes of radar data changed everything we know about tornado structure. On the evening of May 3rd, 1999, while the world focused on the catastrophic F5 tornado that had just devastated Bridge Creek and Moore, Oklahoma, another monster was forming to the north. Official records would rate the Mulhall tornado as an F4, and only 2 people died in its path, which meant it received a fraction of the media attention that night. Guinness World Records would later recognize it as the largest tornado ever measured quantitatively, with a wind field spanning an almost incomprehensible 4.3 miles. What made Mulhall truly special happened in the scientific realm. For the first time in history, researchers were able to deduce the 3-dimensional structure of a tornado, confirming theoretical models that had existed only in laboratories and computer simulations for decades. The data revealed something startling, because the tornado had an internal structure remarkably similar to a hurricane. This video examines the Mulhall tornado in detail, covering its formation, its path, the science that emerged from its observation, and the ongoing controversies surrounding its rating and its records. We will look at the technology that made this discovery possible, the scientists who risked their lives to collect the data, and the small Oklahoma town that lost 80% of its buildings, but almost none of its people. It spent approximately 80 minutes on the ground, left 39 miles of destruction, and in some ways, the Mulhall tornado is still teaching us today. Understanding the Mulhall tornado requires understanding the outbreak that spawned it. May 3rd, 1999 remains the largest tornado outbreak in Oklahoma history. Over a roughly 6-day period from May 2nd through May 8th, 152 tornadoes struck across the Great Plains. And on May 3rd alone, Oklahoma saw more than 70 confirmed tornadoes. That extraordinary number overwhelmed emergency services, media coverage, and the general public's ability to process what was happening. The day began ominously when the first tornado touched down near Medicine Park at 4:51 p.m. Central Daylight Time. What would dominate headlines occurred at 6:23 p.m. when the F5 Bridge Creek and Moore tornado touched down southwest of Chickasha. Over the next hour and 25 minutes, that tornado carved a path through some of Oklahoma City's most populated suburbs, killing 36 people and becoming one of the most intensely studied tornadoes in American history. A mobile Doppler radar unit called the Doppler on Wheels recorded winds of 302 miles per hour within that tornado at 6:54 p.m., a measurement that stood for years as the highest wind speed ever recorded on Earth near the surface. Dissipation came at 7:48 p.m. for the Bridge Creek and Moore tornado. By that point, chaos had consumed the state. Emergency responders were overwhelmed, and television stations had been broadcasting continuous coverage for hours. And yet the outbreak was not over. Far to the north, another supercell had been quietly building strength all afternoon. Meteorologists tracking the May 3rd outbreak designated this second major storm system as Storm B. It would later become known as the Anadarko-Mulhall Cyclic Tornadic Supercell. And according to the National Severe Storms Laboratory, it was unlike anything they had ever seen. The National Severe Storms Laboratory analysis concluded that this supercell's mesocyclone ranked higher in strength measures than any in the mesocyclone detection algorithm database, which dates back to 1994. Thousands of recorded mesocyclones from across the country sat in that database, and Storm B's was the strongest of them all. Formation began in Tillman County around 3:30 p.m. that afternoon. By 4:35 p.m., the first tornado touched down, a brief F0. Storm B was just warming up. Over the next several hours, as it tracked northeast across Oklahoma, the supercell spawned an extraordinary 21 distinct tornadoes. Meteorologists call this a cyclic supercell, a storm that produces tornadoes in repeating cycles, with one tornado dissipating as another forms. Storm B proved exceptionally prolific, and its tornadoes were growing in intensity as the evening progressed. By 9 p.m., Storm B had entered Logan County in north-central Oklahoma. Strong wind shear, abundant moisture, and atmospheric instability that had been building all day created perfect conditions for violent tornado development. That is when something unprecedented happened, unknown to almost anyone, except a small team of scientists in a modified pickup truck. The Doppler on Wheels was a mobile radar system operated by the Center for Severe Weather Research, based in Boulder, Colorado. Dr. Joshua Werman created Doppler on Wheels because he had dedicated his career to getting closer to tornadoes than fixed radar installations could ever manage. Traditional weather radar stations, like those operated by the National Weather Service, are fixed installations positioned to cover large geographic areas. They are excellent for tracking storms over hundreds of miles, but their resolution degrades at close range, and they cannot provide the kind of detailed low-altitude data needed to understand what is actually happening inside a tornado. Doppler on Wheels changed that equation entirely. Mounting a research-grade Doppler radar on a truck allowed Werman and his team to position themselves within a few miles of an active tornado and collect data at resolutions that fixed radars simply could not match. The trade-off was obvious, because getting close enough for good data meant putting yourself in danger. On May 3, 1999, Werman and his team were participating in Vortex 99, a major field research project led by the National Severe Storms Laboratory. Dr. Eric Rasmussen of the National Severe Storms Laboratory served as the project's principal investigator, with Dr. Jerry Straka of the University of Oklahoma as co-principal investigator leading mobile mesonet operations. Historic data from the Bridge Creek and Moore tornado had already been collected by the Doppler on Wheels team earlier that evening, including those record-setting 302 miles per hour wind measurements. As that tornado dissipated and Storm B approached from the southwest, the team made a decision that would prove scientifically invaluable. They repositioned to intercept whatever Storm B was about to produce. At 9:25 p.m. Central Daylight Time, approximately 90 minutes after the Bridge Creek and Moore tornado dissipated, a new tornado touched down 3 miles southwest of Cimarron City in Logan County, Oklahoma. The Mulhall Tornado had begun. From its first moments on the ground, this tornado was different. Visibly larger than typical tornadoes, it was intensifying rapidly as it moved northeast. Storm chaser Roger Edwards, a meteorologist with the Storm Prediction Center, photographed the tornado that night and obtained what is believed to be the only known film slide photograph showing a lightning strike illuminating the funnel. Edwards would later state that the Mulhall tornado may have been as violent or more violent than the F5 Bridge Creek and Moore tornado. The Doppler on Wheels team had positioned themselves along the tornado's projected path, and beginning at approximately 9:36 p.m., they began collecting data from a range of 4 to 9 kilometers. That distance gave them exceptional resolution, while maintaining a margin of safety. What followed was the most detailed radar observation of a violent tornado ever recorded. For 14 minutes, Doppler on Wheels collected high-resolution volumetric data every 55 seconds, scanning up to 1.5 kilometers in altitude. Enormous, violent, and complex, the tornado was finally being observed by scientists who had the tools to see exactly what was happening inside it. Years of analysis would follow those 14 minutes, but the initial findings were staggering. Peak axisymmetric tangential winds, which measure the average rotational wind speed around the tornado's circumference, reached 84 meters per second, or approximately 188 miles per hour, according to the Doppler on Wheels radar. That was just the beginning. Localized Doppler velocities within the tornado exceeded 109 meters per second, more than 244 miles per hour. Analysis of the multiple vortex structure revealed individual wind speeds reaching 115 meters per second, or 257 miles per hour, and some estimates of peak winds within subvortices reached as high as 277 to 299 miles per hour. Context matters here. The original Fujita scale classified F5 tornadoes as having winds of 261 miles per hour or greater, which meant the Mulhall Tornado's measured winds clearly exceeded that threshold. What truly set this tornado apart was its size. The DOW documented a core flow circulation of 1,600 meters, approximately 5,200 feet, which represents the distance between peak velocities on opposite sides of the tornado. Nearly a mile across just for the core, and beyond that core, the tornado's wind field extended much further. The total measured wind field, meaning the area where wind gusts exceeded 96 miles per hour, spanned 7 kilometers or 4.3 miles wide. No tornado had ever been measured with such precision, and none had ever been documented at that size. Guinness World Records 2005 recognized the Mulhall Tornado as the largest tornado ever measured quantitatively. Wind speed and size measurements were remarkable enough, but here's where it gets truly extraordinary. When researchers Dr. Wen-Chao Lee of the National Center for Atmospheric Research and Dr. Joshua Werman analyzed the data using a technique called the Ground-Based Velocity Track Display, GBVTD, they discovered something that had never been confirmed before. The Mulhall Tornado had an internal structure remarkably similar to a hurricane. For decades, tornado researchers had theorized that violent tornadoes might exhibit what is called a two-cell vortex structure, with a central downdraft surrounded by a ring of updrafts and the strongest winds occurring in the annular region between them. This structure is analogous to a hurricane's eye, where calm air descends in the center tiers, while the eye wall contains the most violent winds. Laboratory experiments had demonstrated this structure in vortex simulators, and computer models had predicted it, but no one had ever confirmed it in an actual tornado until Mulhall. The DOW data revealed exactly this structure, with a central downdraft surrounded by rotating updrafts and multiple vortices spinning around the ring like mini tornadoes within the main tornado. At certain times, at least 6 distinct vortices were visible rotating around the main circulation, each containing winds of 260 miles per hour or more. The researchers described it as a miniature hurricane about 1/15 in length scale. Maximum pressure deficit, which measures the difference between atmospheric pressure at the tornado's center and at a radius of 3 kilometers, was calculated at -80 hectopascals at 50 meters altitude. That is comparable to the pressure drop in an intense tropical cyclone. Lee and Werman's landmark 2005 paper in the Journal of the Atmospheric Sciences stated it plainly. For the first time, the evolution and three-dimensional structure of a tornado were deduced using the ground-based velocity track display technique. This was not just a big tornado. This was a window into tornado physics that scientists had been trying to open for generations. While the Doppler on Wheels was collecting its historic data, the tornado continued its relentless march northeast. Approximately 80 minutes on the ground, and 39 miles of travel, crossing through Logan County, Payne County, and Noble County. Damage surveys established an official width of 1,760 yards, exactly 1 mile, though the radar measured wind field extended far beyond that. For much of its path, the tornado passed through largely rural terrain, with open fields, farmland, and scattered homesteads. This rural track was simultaneously fortunate and scientifically frustrating. Fortunate because it meant fewer people in the direct path, and frustrating because it meant fewer structures to document the tornado's true intensity. And then the tornado approached Mulhall. Mulhall, Oklahoma, was a small town of approximately 239 people, located in northern Logan County, about 13 miles north of Guthrie. Zach Mulhall gave the town its name, and his daughter Lucille Mulhall was known as America's first cowgirl. A quiet community, the kind of place where everyone knew everyone. Between approximately 10 p.m. and 10:15 p.m., the tornado passed through or very near the town, and the destruction was catastrophic. Between 78 and 91 homes, representing 60 to 70% of the town's approximately 130 homes, were destroyed or severely damaged. Roughly 80% of the town lay in ruins. The Mulhall Orlando Elementary School was demolished, with only interior walls remaining standing when damage surveyors arrived. When the town's water tower toppled, the resulting flooding pushed at least one house off its foundation. Brian Payne, a tree trimmer who worked the aftermath, described it simply: Mulhall went from a cute little town with trees to just barren. Despite the almost total destruction of the town, something remarkable happened in Mulhall on May 3, 1999. Almost no one died. 2 fatalities and 26 injuries across its entire 39-mile path. That was the official death toll from the Mulhall tornado. Within the town of Mulhall itself, there were no fatalities. How did a town that lost 80% of its buildings lose almost none of its people? The answer lies in warning systems developed over decades, and the individuals who acted on those warnings in real time. Gary England, the chief meteorologist at KWTV Channel 9, had been a pioneer in tornado warning systems. Back in 1982, he became the first television meteorologist to use commercial Doppler radar for tornado warnings. By May 3, 1999, Oklahoma's television meteorologists had developed a culture of aggressive, detailed severe weather coverage that was unmatched anywhere in the country. David Payne, a meteorologist at News 9, described May 3rd as our worst nightmare, but the coverage that night was credited with saving countless lives across the state. Police officers in Mulhall drove through town with their sirens blaring after receiving meteorological alerts, giving residents critical minutes to seek shelter. John Lewis, the Logan County emergency manager, used weather data from the OK First system to track the tornado's approach in real time. Geography played a role as well. Analysis of the tornado's path revealed that while the tornado struck Mulhall with devastating force, its most violent inner core, the section with the highest winds, passed more than a mile south of the town center over empty meadows. The National Severe Storms Laboratory noted, as a credit to the excellent public tornado warnings on May 3rd, only one death was recorded with this storm. Debbie Gooch, a Mulhall resident who survived the tornado in her home, described the experience. It sounded just like a freight train going over. You could hear the quietness, and then it felt just like a freight train, as if you were on the tracks and a train was running over you. She survived because she had taken shelter, and many of her neighbors did the same. The nightmare wasn't over. At 10:45 p.m., the Mulhall tornado finally dissipated 3 miles northeast of Perry in Noble County. For the residents of Mulhall who had survived, there was a brief moment of relief, the kind that comes when you realize you are alive and the immediate danger has passed. That moment lasted 11 minutes. At 10:56 p.m., a second tornado touched down 2.5 miles south of Crescent. This tornado, spawned by a different supercell, carried an F3 rating, and it tracked northeast on a path similar to the Mulhall tornado. By 11:15 p.m., the F3 was striking areas that had already been devastated by the F4. Residents who had emerged from shelters to assess the damage or search for neighbors suddenly found themselves under attack again. This double strike created significant complications for damage surveyors. The National Weather Service assessment noted that damage from the second tornado was indistinguishable from damage caused by the earlier F4 tornado, and in areas where both tornadoes had passed, determining which tornado had caused which damage became nearly impossible. One of the most dramatic moments of that night occurred during the interval between the two tornadoes. An ambulance was transporting a critically injured tornado victim toward Guthrie when emergency management officials detected the second tornado approaching on an intersecting path. Using real-time tracking, they were able to stop the ambulance until the tornado passed just in front of it, a near miss that underscored both the danger of that night and the life-saving potential of accurate tracking. John Lewis, the Logan County emergency manager, had to relocate his rescue command centers twice as successive tornadoes followed similar paths through the area. Measured winds exceeded 257 miles per hour, with estimates suggesting peaks as high as 277 to 299 miles per hour. Why then was the Mulhall tornado rated F4 and not F5? This question has been debated in meteorological circles for more than 2 decades, and it goes to the heart of how we measure and classify tornadoes. The Fujita scale, which was in use in 1999, rated tornadoes based on observed damage rather than wind speed measurements. An F5 rating required damage consistent with winds of 261 miles per hour or greater, specifically the kind of catastrophic structural damage that would indicate such extreme winds. Geography created the problem with the Mulhall tornado. The tornado's most violent inner core, the section where those extreme wind speeds were recorded, passed primarily over rural terrain, meaning empty fields, meadows, and areas with no structures to damage. Tim Marshall, the Texas Tech University meteorologist and storm damage engineer who led one of 3 damage survey teams, had nothing to survey in the areas where the highest winds occurred. When the tornado did strike structures in Mulhall, it caused catastrophic damage, but the F4 damage indicators were sufficient to explain what surveyors found. Structural evidence in the direct path of the highest winds simply did not exist in sufficient quantity to justify an F5 rating under the methodology of the time. Roger Edwards, who analyzed the tornado extensively, stated clearly that it may have been as violent or more violent than the F5 Bridge Creek and Moore tornado. The mesocyclone that spawned it was the strongest ever recorded in the NSSL database, and the Doppler on wheels, DOW, measured winds that exceeded F5 thresholds. Without damage to document those winds, the rating could not be upgraded. This highlights a fundamental limitation in tornado rating systems, because we rate tornadoes based on what they hit rather than what they are capable of doing. A tornado that passes over open prairie might be just as violent as one that strikes a city, but only one of them will receive a rating that reflects its true intensity. The Mulhall tornado, by this measure, was likely underrated. The Mulhall tornado's claim as the largest tornado ever measured has also been subject to debate, particularly after the El Reno tornado of May 31st, 2013. The El Reno tornado, which struck Canadian County, Oklahoma, and tragically killed several storm chasers, was measured at 2.6 miles wide, and that width was verified by ground damage across its full extent. EF1 or greater winds were confirmed across that entire span through the damage path itself. The Mulhall tornado's 4.3-mile width measurement refers to something different, specifically the radar-detected wind field, where gusts exceeded 96 miles per hour. The actual damage path was only 1 mile wide. Which tornado was larger? The answer depends entirely on how you define size. Measuring the total wind field detected by radar puts Mulhall ahead at 4.3 miles versus El Reno's approximately 2.6 miles. Measuring the verified damage path on the ground puts El Reno ahead. Most official sources, including the National Weather Service, recognize El Reno as the widest tornado on record because its width was verified by ground damage rather than radar estimation alone. This distinction matters because radar measurements can capture wind speeds at altitude that may not reach the surface with the same intensity, and the threshold for measurement of 96 miles per hour. Gusts for Mulhall is lower than the threshold for damage verification. None of this diminishes the Mulhall tornado's size. A wind field 4.3 miles wide, with multiple vortices containing winds of 260 miles per hour, is almost incomprehensibly large. Understanding what that measurement means and how it compares to other measurements using different methodologies is what matters. The Guinness World Records. Recognition of Mulhall as the largest tornado ever measured quantitatively remains valid, as it was the largest tornado measured by mobile Doppler radar at the time, and the measurement was revolutionary. Whether it was larger than El Reno depends entirely on what you are measuring. The 14 minutes of data collected by the Doppler on wheels on May 3, 1999, have had an impact far beyond that single night. The Lee and Werman 2005 paper, published in the Journal of the Atmospheric Sciences, has been heavily cited in tornado research. The Mulhall dataset has been referenced in approximately 70 peer-reviewed scientific publications and remains foundational for multiple areas of study. Tornado vortex dynamics research has been transformed by the Mulhall data because the confirmation of a two-cell vortex structure with a central downdraft surrounded by updrafts validated decades of theoretical work and gave researchers a real-world benchmark for their models. Wind engineering simulator studies have used the Mulhall measurements to calibrate laboratory vortex simulators, ensuring that the artificial tornadoes created for research purposes accurately reflect the behavior of real violent tornadoes. Multi-level tornado measurement analysis, which focuses on understanding how wind speeds vary from the surface up through the tornado's height, advanced significantly through the Doppler on wheels. Volumetric scans that capture data at multiple altitudes simultaneously. Computer models that simulate tornado formation and behavior can now be tested against the Mulhall data to verify their accuracy, which has benefited tornado simulation model validation enormously. Dr. Joshua Werman and the Center for Severe Weather Research have continued their work in the years since Mulhall. Werman has been featured in numerous documentaries and television programs, including PBS Nova's The Hunt for the Super Twister, the Discovery Channel's Storm Chasers series, and the National Geographic Channel's Tornado Intercept. The Mulhall tornado itself was featured in the Weather Channel program Oklahoma Tornado Target in 2016 and was analyzed in the FEMA Building Performance Assessment Team report on the 1999 Midwest tornadoes. Behind the statistics and the scientific papers, there were people. Gordon, a Central Electric employee who witnessed the tornado from approximately 10 miles away, described what he saw. He said it was the most ominous tornado. We were 10 miles from the tornado, and it took up the whole windshield. He added that when they saw the tornado, they were behind it, and it was like the sky came to the ground. Myers, another Central Electric employee who participated in the response, described finding a vehicle in the aftermath. He said he saw a big slab of metal in a bar ditch. It took him a few minutes to understand what it was, but that ball of metal was a Chevy pickup truck that could fit in the back of his truck. Hank Brown, a News 9 storm tracker, described the surreal nature of the damage. The debris path was unreal. On one side of the street, the neighborhood was pristine, with freshly mowed yards, and on the other side of the street was just utter destruction. Jack McAnally was a Mulhall resident who lost everything, and he described the morning after. He said when daylight came, you got a real good look at it. You're thinking, oh God, we got a lot of work ahead of us. McAnally also captured something important about human resilience when speaking years later. He said it's taken us several years. The first 5 years is the most traumatic. But after 5 years, you start to think, hey, I think this is going to come back together. The Doppler on Wheels team itself was not merely passive observers. According to accounts from that night, while collecting their historic data, they simultaneously worked to direct vehicles out of the tornado's path. Scientists they were, but also people trying to help. Mulhall has rebuilt. The town that lost 80% of its buildings on May 3rd, 1999, received a new water tower to replace the one that was toppled. A new school replaced the demolished Mulhall Orlando Elementary, and new homes rose where rubble had been cleared. Census data tells part of the story. In 2000, the year after the tornado, Mulhall's population was 239, and by 2020, it had declined slightly to around 212 to 220, which is not dramatically different and is consistent with broader rural population trends across Oklahoma. Other indicators show growth, with the median household income in Mulhall rising from $31,750 in 2000 to $73,929 in recent years. Median home value increased from $61,400 to $96,165, and per capita income more than doubled, climbing from $13,804 to $32,371. According to available data, 24.7% of current housing units in Mulhall were built after 2000, a reflection of the reconstruction that followed the tornado. One small detail captures the spirit of Mulhall's recovery. A pastor from Mississippi came to the town as a volunteer during the relief efforts after May 3rd, and he was so moved by the community that he stayed and eventually became the permanent pastor of First Baptist Church. The May 3rd, 1999 outbreak is extensively commemorated in Oklahoma. The 25th anniversary in May 2024 saw special coverage from multiple Oklahoma television stations and formal commemorations from the National Weather Service in Norman, while the 20th anniversary in 2019 featured comprehensive retrospectives with survivor interviews. Most of the memorials and commemorations focus on the Bridge Creek Moore F5 tornado, which caused 36 deaths compared to Mulhall's 2. That is understandable, given that the human toll demands recognition. In scientific circles, the Mulhall tornado's contribution to our understanding of these storms is equally remembered. The Mulhall tornado teaches us several important lessons, while also revealing the limitations of our measurement and classification systems. First, it demonstrates that our tornado rating system is fundamentally a damage-based system, rather than a wind-based system. A tornado's rating reflects what it hit, not what it was capable of doing. The Mulhall tornado almost certainly produced F5 intensity winds over portions of its path, but because those winds passed over empty fields rather than structures, the evidence did not exist to justify an F5 rating. This creates an inherent bias in tornado records. Tornadoes that strike populated areas are more likely to be accurately rated because there are structures to damage, while tornadoes that pass over rural terrain may be systematically underrated because there is nothing to document their true intensity. Second, the Mulhall tornado shows the extraordinary value of mobile research platforms like the Doppler on Wheels, known as the DOW. Fixed radar installations simply cannot provide the resolution and low altitude coverage needed to understand tornado structure. 14 minutes of data collected on May 3rd, 1999, have advanced our scientific understanding more than decades of fixed radar observations. Those measurements also have limitations worth noting. Doppler radar analyzes the motion of debris particles and returns statistical ranges of velocities rather than precise point measurements, and the DOW data was collected at altitude rather than at ground level. Researchers have noted that the DOW often found winds higher than the tornado's damage indicated, a reminder that peak winds occur over very limited areas and would affect fixed observers for only fractions of a second. Third, the Mulhall tornado demonstrates the life-saving power of effective warning systems. A town that lost 80% of its buildings suffered no fatalities within its limits, thanks to police officers driving through town with sirens blaring, emergency managers using real-time data to track the tornado, and television meteorologists providing continuous coverage. All of these elements worked together to give people the time they needed to take shelter. The National Severe Storms Laboratory concluded that, as a credit to the excellent public tornado warnings, on May 3rd, only one death was recorded with this storm. More than 25 years after the Mulhall tornado, questions remain. Was it truly an F4, or should it have been rated F5? Wind measurements suggest F5 intensity, but the damage methodology of the time could not support that rating. The enhanced Fujita scale, introduced in 2007, might have changed that assessment, but the tornado occurred under the original system, and ratings are not typically revised retroactively. Was it the largest tornado ever? By radar measurement of the wind field, yes, as 4.3 miles remains the largest quantitatively documented. By damage path width, no, as the El Reno tornado's 2.6-mile damage path is larger. Both claims are defensible, depending on the criteria used. Could a tornado actually be that large? The Mulhall data confirmed that, yes, violent tornadoes can extend their damaging winds across areas that seem impossibly wide. The wind field measurement was not an error or an artifact. It was a genuine observation of a genuine phenomenon. These questions matter because they inform how we prepare for and respond to tornadoes. If violent tornadoes can be significantly larger than their damage paths suggest, our safety zones may need to be expanded. If radar measurements can detect wind fields that do not produce corresponding ground damage, we need to understand why and what that means for warnings. The Mulhall tornado does not answer all of these questions, but it provides data that researchers continue to analyze and debate, refining our understanding with each new study. On May 3rd, 1999, the Mulhall tornado traveled 39 miles across central Oklahoma, destroyed 80% of a small town, killed 2 people, and provided scientists with the most detailed observations of a violent tornado ever recorded. DOW measurements revealed a wind field 4.3 miles wide, winds exceeding 257 miles per hour, and an internal structure resembling a miniature hurricane, confirming theoretical models that had existed only in laboratories and computer simulations. The official rating came in at F4 because the most violent winds passed over empty fields with no structures to damage. It may well have been an F5. We will never know for certain because the damage-based rating system could not capture what happened over those empty meadows. Mulhall rebuilt. New homes, a new school, a new water tower. Population remained stable. Incomes rose, and life continued. A pastor from Mississippi who came to help stayed to become part of the community. The scientists who collected the data published their findings, and those findings changed how we understand tornado structure. The Lee and Werman 2005 paper has been cited in dozens of subsequent studies, and the Mulhall dataset remains a benchmark against which models are validated and theories are tested. Debate continues about ratings, about records, and about what those 14 minutes of data really tell us about the nature of violent tornadoes. The Mulhall tornado was overshadowed on May 3rd, 1999, by the more deadly F5 that struck Bridge Creek and more, receiving less media attention, fewer memorials, and less public recognition. In scientific terms, it may have been equally significant, perhaps more so because of what it taught us. This was a tornado that science almost missed. The Doppler on Wheels team had already collected historic data from the Bridge Creek and Moore tornado, and they could have called it a night. Instead, they repositioned to intercept Storm B, and they captured something unprecedented. 14 minutes of data. a wind field 4.3 miles wide. The three-dimensional structure of a tornado revealed for the first time. The Mulhall Tornado lasted approximately 80 minutes, and its scientific legacy has lasted more than 25 years and continues today. That is the power of being in the right place at the right time with the right equipment, and having the courage to stay when every instinct says to run.